Hello guys, welcome back to my channel. Today I'm going to be doing an integral involving the gamma function. So let's get to it without further ado. So we have our original problem, let's call it I, which is defined as the integral from 0 to 1 of the natural log of the gamma of x dx. Well, now before proceeding with anything, I would like to just tell you that it's the gamma function that we are dealing with. So whatever we do, we have to be sure of our approach, because gamma is like a serious business. So now looking at this crazy integrand, what are we going to do? Well, we can't certainly use any elementary integration techniques. They're going to fail us. So we need to be armed with certain facts. So the most important fact is what's called Euler's reflection formula. So what that states is, say you have the gamma of x multiplied with the gamma of 1 minus x, that just equals pi over sine of pi times x. Yes, it's a really beautiful formula. Now, what if we were to take the natural log on both sides? Say if we have the natural log of the gamma of x times the gamma of 1 minus x being equal to the natural log of pi over sine of pi x. Now we can use certain properties of logarithms. I'll remind you again, as I do in most of my videos, that say if you have the natural log of a times b, you can split it up as the natural log of a plus the natural log of b. And if you have, say, a quotient, say the natural log of p over q, that can be written as the natural log of p minus the natural log of q. So I'm going to implement these very same identities when I split whatever we have over here. So we're going to be left with the natural log of gamma of x plus the natural log of the gamma of 1 minus x being equal to the natural log of pi minus the natural log of sine of pi x. Well, what does this look like? Our original integrand, right? I mean, well spotted, because now we can integrate, we can do a definite integral on both sides from say 0 to 1. So integral from 0 to 1 of, because that's what exactly what our problem was, right? It was an integral from 0 to 1 of the natural log of gamma of x. So we have the natural log of gamma of x dx plus, we can split it up into two integrals by the linearity of this integral, plus the integral from 0 to 1 of the natural log of gamma of 1 minus x being equal to the integral, don't forget the dx, integral from 0 to 1 of the natural log of pi dx minus the integral from 0 to 1 of the natural log of sine of pi x dx. So we have a left side that we need to evaluate, and we also have a right hand side that we need to evaluate. So I'm going to do them separately. So first let's look at what the left hand side is. So on the left hand side we have integral from 0 to 1 of the natural log of gamma of x dx plus again the integral from 0 to 1 of the natural log of gamma of 1 minus x this time dx. Well, we know what this is, right? We just defined it earlier to be I, this part. But now what is this? Say the integral from 0 to 1 of the natural log of gamma of 1 minus x dx. Why don't we try to do a u substitution? Say we let u equals 1 minus x such that du is equal to negative dx, and let's fix our upper and lower bounds. So when x equals 0, we have u being equal to 1, and when x equals 1, we have u being equal to 0. So essentially we have I plus the integral from, well, this time it's going to be 1 to 0, right? We just found that out over here separately. Integral from 1 to 0 of the natural log of gamma of u, and dx is basically negative du. So negative du. Now you might remember one of the properties of definite integrals is we can flip the upper and lower bounds by multiplying with a negative. So say let me again remind you of this identity. Say we have the definite integral from a to b of say f of x dx. This, the upper and lower bounds of integration can be flipped by multiplying a negative, and then you get integral from b to a of f of x dx. So I'm going to implement the same trick over here. So finally we're only left with the integral from 0 to 1. Because of the negative I can flip the upper and lower bounds of the natural log of gamma of u du. Now there was another property in definite integrals, that the variable doesn't matter. Whatever the variable we had, as long as the upper and lower bounds are the same and the integrand is the same, it doesn't matter what variable we have. So for example, if we had the integral of x squared dx from say 0 to 5, that's the same thing as the integral from 0 to 5 of y squared dy. So essentially the variable doesn't matter because the form of the integrand is the same and upper and lower bounds of integration are the same. So we can write everything in terms of x. So we have the natural log of the gamma of x. Instead of du we have dx now. And what is this? That's right, it's I again. So we have I plus I being equal to 2i. And what is this? What is everything? What is all of this equal to? The left hand side, right? The left hand side is basically 2i, 2 times our original problem. Well, great. Now let's do our right hand side. So on our right hand side we obtained the integral from 0 to 1 of the natural log of pi dx minus the integral from 0 to 1 of the natural log of sine of pi times x dx. Now the natural log of pi is a constant, so you can just bring it outside. Natural log of pi, and then you only have the integral from 0 to 1 of dx. And why don't we do a little substitution here? So why don't we let u equals pi x such that du is nothing but pi dx, and when x is 0 u is 0, when x is 1 u is pi. So we have a definite integral being equal to integral from 0 to pi of the natural log of sine of u. So u instead of pi x, and instead of dx we have 1 over pi times du, right? Just rearrange this thing. So 1 over pi times du. Well, we can evaluate this. We have the natural log of pi times x being evaluated from 0 to 1 minus 1 over pi is a constant times the integral from 0 to pi of the natural log of sine of u du. Now we can easily calculate this. When we plug in 1 instead of x, we have 1 times the natural log of pi, and when we plug in 0, we have a 0. So essentially we are left with 1 times the natural log of pi, which is the natural log of pi minus 1 over pi times the integral from 0 to pi of the natural log of sine of u du. So all we are left to do is to evaluate this integral. What is this integral? Well, I had covered this up in my last video. So in case you don't remember, I'll give you a, well, it wasn't exactly the last video, but I had made a previous video. I don't know when, but I can probably provide a card over here right now. But it was some last video. But I mean, I definitely say I don't remember when I shot the video, so I think you guys don't remember what the answer was. So I'll just give you a trip down memory lane quickly. So in one of the videos, I had calculated the integral from 0 to pi over 2 of the natural log of sine of x dx to be negative pi over 2 times the natural log of 2. Well, instead of going from 0 to pi over 2, we are going from 0 to pi here of the natural log of sine of x dx. Now, because of the symmetry of the natural log of sine of x function, the integral from 0 to pi of the natural log of sine of x dx is just twice of the integral from 0 to pi over 2 of the natural log of sine of x dx. And we know the value of this, right? 2 times this thing, so we just have a negative pi times the natural log of 2. And by properties of definite integration, we can again change the variable without destroying the meaning of this absolute integral, this definite integral. So we know the value of this thing. Well, great, let's plug everything back now. So we have our right side being equal to the natural log of pi minus 1 over pi, and we just found the value of this thing. That's negative pi times the natural log of 2. Well, the negatives become positive on multiplication. The pi's cancel out, and all we are left with is the natural log of pi plus the natural log of 2, which you can write by virtue of log properties as the natural log of 2 pi. Well, that's our right hand side, right? We want our right hand side to equal our left hand side. So let's recombine everything for the grand finale. So we had our LHS equals RHS, our right hand side equals our left hand side. So our left hand side, if you remember correctly, was 2 times the original integral, the original problem. And that is equal to, we just calculated the right hand side to be the natural log of 2 pi. So our original problem, which we defined as I, is nothing but half of the natural log of 2 pi, which, if you remember some log properties, say you had natural log of a to the power b, you can write this as b times the natural log of a. So instead of b, we have a half. So it's going to be the natural log of a to the half power, which is basically the square root. So the natural log of the square root of 2 pi. And well, what was our I? The integral from 0 to 1 of the natural log of gamma of x dx is equal to the natural log of square root of 2 pi. And before ending the video, just an interesting fact. the derivative of this integrand, so the derivative of the natural log of gamma of x is nothing but gamma prime of x over gamma of x. I just use the chain rule here, and that is nothing but the digamma of x. So integrating this thing is basically doing one integral to remove this derivative operator, and then another definite integral from 0 to 1. So it's basically some sort of double integral on the digamma function. Now, using the definition of digamma, say for example using um, the series representation of digamma of x, yields some sort of convergence problems. So otherwise we could have easily done that, but it seems that Euler reflection formula is a way more efficient solution. I mean, if you can show somehow that that the double integral of this digamma function, first just the regular antiderivative and then a definite integral from 0 to 1 of the antiderivative of the digamma of x with respect to x, will yield the natural log of square root of 2 pi. I would probably best prefer leaving that as an exercise to the viewers, you guys. Please comment down if you use that approach and come up with an answer, because as far as I'm concerned, this seems like something that you would get out of, say, a zeta regularization. So you might want to watch out for something like n equals 1 to infinity of, say, the natural log of n. So it's like basically natural log summed with itself like infinite times, basically yielding an infinite product of terms, and that by the same zeta regularization is nothing but whatever we obtained over here, half of the natural log of 2 pi. So you might probably end up with something like this. In the conventional sense, an infinite product like this is divergent and is like undefined, but with zeta regularization and regularization of these special functions, even say gamma regularization for that matter, we might assign some values to these crazy, in the normal sense, divergent infinite series. So I mean, just to close it down, to give you some perspective, I actually tried to find, as I said, the double integral of the digamma function by say using the digamma series, for example, which is negative gamma, Euler Mascheroni plus the infinite series from, say, n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus x. Well, I tried using this, and finally I successfully calculated the antiderivative by this series, and was actually doing a lot with with the second integral. And then when I plugged in the upper and lower bounds, I happened to obtain this very regularized term, natural log of square root of 2 pi, but I was also obtaining a divergent term of the natural log of k, the limit as k approaches infinity, which is basically just blowing off to infinity, and then a stray one added with the entire thing. So if you're gonna try to evaluate the same problem using this method, and if you get the answer somehow, please comment down. It will be really enlightening even for me. But any reason why any reason why we can't obtain the same value as we did with our Euler reflection formula approach is because of the probably the fact that there is some uniform convergence problems. Say if we we can't properly justify the interchange of the limit and the sum using Fubini-Tonelli or the dominant convergence theorem. So that could be one of the things, because we had an infinite sum from n equals 0 to infinity, as I just showed you a moment ago. So that could definitely be one of the problems. But so for me, I don't think that we can find the same correct answer using the infinite series for the Digamma function. But in case you do, please feel free to comment down, or make a video and then send the link in the comments. Up to you. So that's it for this video, guys. Please like, share, and subscribe. Recommend me to your um, number file friends. And peace out. Stay in. Stay safe.